In this video series, The Blocks in Blockchain, we're going to look at why consensus doesn't scale.
In this simple example, we'll be looking at a network of nodes that share a blockchain or distributed ledger. Taking a closer look at three of the nodes, we have one that will create and sign its transactions and then broadcast them to the network. The other two nodes will receive the transactions and validate and vote on them. Each of the nodes will then send their votes into the network, and it is the responsibility of every node to verify and count the votes and ensure that the network has reached consensus. In a process not described in this video, those transactions will be organized into the next block to go into the blockchain. The blockchain is a mathematical hash-linked chain of blocks. Once the new block is added, the new blockchain is shared with the network. Yet, while this process seems relatively simple, the question is, why doesn't consensus scale? Well, let's do some analysis. Considering one transacting period, if each node creates 10 transactions, each node has to create and sign its own transactions, validate and vote on the other node's transactions, while verifying and counting all the other nodes' votes. With these activities, let's consider the number of nodes, the number of transactions, and then the total computations per node. With the first example of two nodes, there are 20 transactions. 10 are created and signed by each node. They validate and vote on the other node's transactions, and they verify and count the votes from that node, leaving a simple total of 30 computations per node. With three nodes, there are 30 transactions. Each node has to create and sign its own 10 and validate and vote on the 20 transactions from the other nodes. But now this means every node has to verify and count 40 votes, which totals 70 computations. With four nodes, there are now 40 transactions. Each node creates and signs its 10 and has to validate and vote on 30 transactions. But this means it has to verify and count 90 votes, which leaves a total computations of 130. If the network expands to 5 nodes, there are 50 transactions. Again, create and sign 10, validate and vote 40, but have to verify and count 4 times 40 votes, which is 160. Now the total computations are 210. So what we see is that as the transactions increase linearly, i.e. at the same amount for each increase in node, the total computations are expanding exponentially at an accelerating pace. So let's graph this to demonstrate it visually. There are the number of network transactions and the computations per node on the y-axis and the number of nodes on the x-axis. The total number of network transactions increases from 20 to 50 as a straight line. It's a linear progression. The computations per node, however, expand exponentially. 30 with 2 nodes, 70 with 3 nodes, 130 with 4 nodes, and 210 with 5 nodes. You can see the acceleration of the line upwards. So, we conclude from this that with an increasing number of nodes, the number of computations per node increases exponentially. And also, the time for the network to reach consensus also increases exponentially, without including the time to broadcast and receive the transactions and votes. So imagine a market with 350 nodes creating 10 transactions per second each. The blockchain network would have to process 3,500 transactions per second. Each node would need to create and sign 10 transactions per second, but validate and vote on 3,490 transactions per second, while verifying and counting 1,218,010 votes per second. This is huge. but on an average day, the DTCC clears 3,500 transactions per second in the US market. So we've shown that consensus doesn't scale. And any blockchain or DLT solution using consensus doesn't scale either. So this means a DLT solution needs to scale linearly. And a viable DT solution needs to achieve consistency without consensus. If you want more information on a viable DLT solution or to contact us, go to l4score.com. Thank you.